Hi, good morning. This is going to be a series of two lectures on Lagrange multiplier. As usual, the first lecture will be spent to understand what the theorem is about, Lagrange multiplier trick is about. Okay, and in the second lecture, perhaps I will give you a proof of that. And if time permits, I'll give one of my favorite applications. Okay, and yeah, the references are a forthcoming book of mine on analysis and RN. But there are already two articles. One article is called Lagrange Multiplier, a geometric treatment. Okay, and second one is the implicit function theorem, where it deals with the implicit function theorem of only two variables. But towards the end, I give typical applications of Lagrange multiplier, very easy applications, but they bring out the geometry, what the multiplier trick is about. So, because I will touch upon some of these things in this lecture, but I don't want to spend too much time, and motivated by my talk, I hope you will be tempted and encouraged to read those articles. Okay, yeah. Now let us share and start the work. Yeah, the first thing one should start is, if you have been following my lectures on differentiation on R again on Rn, you would know the following result. If u is an Rn, okay, and to R, okay, this is, let's say, as a differentiable. All right, okay, then we say a point A in U is a local extremum, that is maxima or minimum of F if there exists an open ball, okay, and this is my A, this is open ball. So that what happens there, so that F, okay, has an extremum at A in BAR. Of course, that we are assuming this is contained in U. Okay, then what we know is, if A is a local extremum of F, then derivative of F at A is 0. That is, the gradient of F at A is a 0 vector, which is same as saying all the partial derivatives at A are 0. These are all the known things. Okay, but in general, if F may be differentiable, for example, let us look at f of 0 1 to R and f of x equal to x. Then the point A equal to 0, the B equal to 1, they are the actually maximum. This is the minimum, and this is global minimum, and this is the global maximum. What do you mean by global? That is for every x in the domain, okay, fx is less than or equal to f of 1, and similarly fx is greater than or equal to f of 0, right? And 0 and 1 are not local maximum, local extrema. 0 and 1 are not, okay, and therefore you look at f dash of 0, f dash of x, 1 for every x. In particular, f dash of 0 is 1, which is also f dash of 1, right? Therefore the derivative need not be 0. That's the first observation. Okay, second observation is, suppose I have a set S in Rn. Okay, let me assume S is contained in U, where U is open in Rn. And further assume F from U to R is differentiable. Okay, let me just check. It's recording, right? Okay, so let's assume that A is in S, so that F is a local, let us say, maxima, the same thing, okay, maximum for F in S. That what does that mean? So this may be my U, and this may be my S, and this may be my A. When I say it's a local thing, what I need is, you start with an open set containing A, right, and intersect with S. Therefore, what do I have? This object. Okay, so this is a open subset, open neighborhood of A in the set S in subspace topology. You understand? Therefore, what I mean is, for every X where in, let us call this as some BAR if necessary, okay, U intersection, S intersection BAR, okay, my Fx is less than equal to Fa. So you understand the local natures with respect to subspace topology of S, right? Can I expect the derivative of Fa is 0? Okay, remember the set S may not be open. If S were open, then among BAR intersection S will again be open, therefore we will be in good shape. You understand that? So a typical example, let us look at again an example to make sure that we all follow what is happening. Let me look at my S, set of all x in Rn, so that x dot x, that is summation xi squared 1 to n equal to 1. And let me look at the function f, which is defined on Rn to R. Okay, f of x is xi, right? Now you can see the point P equal to, let us say, E1 x1, sorry, this is x1, the first coordinate. Okay, x equal to x1 to xn, that's the first coordinate, right? Then at that point, what is f of P? That is 1, right? And for every x in S, notice that S itself is open in S, right? Therefore, right, okay, I can take to be a ball of huge radius B, okay, B02 intersect with this will be S itself, right? And for every x, what do I have? F of x equal to x1, right? But that x1 is less than equal to mod x1, but mod x1 is less than equal to, okay, xi squared to the power half, right? That's less than equal to 1, that's equal to 1. You understand? Therefore, what I have is fx is less than equal to f of p for every x in S, right? Now what is the gradient of f? At any point, gradient of f is 1, 0, 0. In particular, for any x, actually, delta at any point, delta f at any x is actually 1, 0, 0. So in particular, it's not 0. You follow that? Yeah. So what really happens? This is what we understand. So is there any kind of first derivative test to understand something about the local maxima minima of a function f depend only on a set S, which need not be open set? Okay, Lagrange multiplier theorem deals with, okay, the such problems of when S is a local, it's a level set or level surface. What does that mean? Remember, you had already seen the, even though I have not introduced the word level set, level surface in the case of implicit function theorem. Suppose G is a function from U to R, Rn is open of course, and assume C1. Let me assume, okay, there is a point P in U such that G at P is 0. I may also call P equal to A sometime, okay, G at 0, right? Then what we found out was, in implicit function theorem we put a condition, right? Namely, the derivative of f at this point should be of maximal rank. The possible maximal rank is 1. Therefore, what do I mean is delta f at P is not equal to 0, right? Then let's look at the so-called level surface that of all x in U such that fx equal to 0. This is called level surface of f at a level 0. See, it could be actually some constant c, then it will be level c. F of x equal to c, then I will say this is f inverse of 0. If it is f inverse of c, then I call c as a level. Okay, we understand this. For convenience sake, we always denote it by 0. Okay, why it's called level? That's also easy. Suppose let us look at f from R3 to R. right? F of x y z equal to z. Then let's look at f inverse of 1. What is this? This is the plane at z equal to 1, right? This is z equal to 1 plane, and f inverse minus 1 will be below. This will be z equal to minus 1. So what is the level of the plane? From the xy plane, it is at level 1. That is why it's called level. Okay, you can do mathematics without learning any of these things also, because that's what usually many teachers do, but it's good to understand why it happens so that it gives you some kind of geometric idea. Okay, so what is the thing is the following. Suppose I have a function f from u in Rn to Rn, which is C1. Okay, let G also be a function f from u to R, which is also C1. Okay, assume 0 is the value, range is in the range of G, right? Then I can denote by G inverse 0, which is my level set of G. Okay, and what we are going to assume is that, okay, suppose A is a point in S, so that F has a local extremum, okay, at A, and local, this is with respect to S, that is in the subspace topology. Just go back to the picture, you should understand. All right, you follow that? Okay, now what we are going to assume is our gradient delta G at A is non-zero, that is dg of A has rank 1. Remember, G takes values only in R. Yeah, right. Then what do I want to say? Okay, then what we want to say is this delta, suppose what is our assumption? F as a local extremum. So we do, okay, we now saw this may not be 0, but what we want to conclude, we want to conclude the following, that is, there exists a scalar lambda so that the gradient of f at A equal to lambda times gradient of G at A. Okay, please understand, this is what we conclude. We do not conclude this is equal to 0, the gradient of f at A, but we know it is a gradient must be a scalar multiplier of the gradient of G at A. Just think, okay, why do we use first derivative test in real analysis or anywhere? We try to find out what are the points at which the function has a local extrema, right, maxima or minima, local maxima, minima. That is, we compute, we find points x so that d of x, that is derivative of f at x, is equal to 0. So that gives us the kind of possible points, okay, prospective points at which the function may have a local extrema, right? So now this gives an idea. Suppose now I have a function f, okay, so I want to know what kind of a local extrema it has on the level set S. Please keep the picture in mind, don't. Okay, on this set S, I want to look at point A so that A is a local minimum for f in S, right? So what does it say? Now you see that it replaces the standard first derivative test of calculus. What does it say is, you compute the gradient of f at A and compute the gradient of G at A, okay, and try to find whether this is a scalar multiple of this. Okay, then such an A is a likely candidate for local extrema of f on S. Please pause, review, understand, play the thing. Did you understand? I took f dash x equal to 0, that gives me possible local extrema, local maximum, minima for a real valued function of a real variable. Now what do I have? I have a function f which is defined on open set, but I am not looking at the local extrema there. Okay, I am looking at only on the set S, which is the level set. Okay, this is called the constraint with respect to the constraint G. Okay, so I don't want to say f, so I should have a local maxima minima on U, but it is subject to the constraint. Okay, the point x has a constraint, namely g of x equal to 0. Okay, at such point, how do I locate such points where it has a local extrema with respect to s only on the level set s? It says that compute the gradients of g and f, and you find the point a at which the gradient of f at a is a scalar multiple of gradient of g at a. Okay, that a is a likely candidate. We are not saying it will be. It's a likely candidate because a necessary condition, right? That's what we are going to do. Have you understood? Yeah. Okay, let's quickly do one trivial example. Okay, suppose I want to find, okay, f is a function from, let us say, R2 to R. Okay, f of x equal to xy equal to x squared plus y squared. Now what do I want? I want to find, okay, my g is again R2 to R, so that g of xy equal to x plus y equal to 1, x minus equal to 1, therefore g inverse of 0. What is this? This is a straight line. Now let's try to understand. This is a straight line. This is x plus y equal to 1. This is my point 1 comma 0. This is a point 0 comma 1. Right? Now this is, so what is the level set of g at 0? That is nothing else than straight line x plus y equal to 1. So what am I looking at? I want to find the maximum minimum. So notice that on R2 it has only one minimum, namely 0 0, because after that it keeps on going to infinity, right? Therefore there is no maximum. And similarly, let us look at the constraint. So what I am looking at, I am trying to find out, take various points here, okay, and I want to find f of that point. F of that point is nothing other than the distance of that point square, distance squared of that point to the origin, right? That is d of xy 0 0 squared. That is your f of xy. Yeah. So again, if you look at the picture geometry, you know, again f has no, okay, even when I restrict f to only this line, okay, it can go to infinity as I go along this way it will go to infinity. Therefore I should expect only some kind of a minimum, okay, respect to that. You follow that? And notice that it may not be a minimum for f on R2 because that I know it is 0 0. Yeah. Okay, now how do I find it? Let us look at the theorem. The theorem said I have to look for the gradient of f. What is the gradient of f at any point xy? That is 2 times xy. Remember, g of xy is x squared plus y squared. Therefore, its gradient is 2x 2y. And what is the gradient of g at xy? That is x plus y minus 1, right? Therefore, it is 1 comma 1. So, what do I want? Okay. So, I want to know, okay, find a lambda so that delta fxy equal to lambda times del nabla xy. Okay, but this is 2xy should be equal to lambda lambda. You understand? This is same as saying some other lambda, xy equal to lambda lambda. That means x must be equal to y. Do you follow that? Yeah. So we found a point. Okay. I also know what should be lambda. That we will find out. Have you understood this? So we do not know lambda. It has to be this. Suppose such a lambda exists, then this 2 times xy must be equal to lambda times 1 1, which is lambda lambda. Okay. All right. So suppose there is a lambda, so that this happens, that what does that mean? My x must be equal to y as a corollary. Do you follow? But then remember, where does xy lie? The point xy lies on the level set. That means x plus y equal to 1. That means 2x equal to 1 or x equal to y equal to half. Yeah, therefore I know what is the minimum. Okay, the minimum is attained at this point. Okay, this will be half of. Yeah, have you understood? Okay. So there are few more points, there are few more examples I can work out, but let me try to understand this one single example, try to explore a little more. Okay, all these things will be useful if you want to go into geometry or topology, and also you will have a thorough understanding of Lagrange multiplier. Now let us do that. What is it I want to do? I want to do f of xy equal to x squared plus y squared. I wanted to find maxima minima subject to the constraint x plus y minus 1 equal to 0. Right? That means my y must be 1 plus x. 1 y equal to 1 minus x. Right? If xy lies in the level set, that is a level surface, then necessarily y must be 1 minus x. Do you understand? Because xy should satisfy x plus y equal to 1. That means y equal to y minus x. Therefore, okay, so whenever xy lies in S, I am going to look at the maxima minima of fxy. Therefore, my function f of xy actually becomes a function of one variable x squared into 1 minus x whole squared. This is what I have to minimize. Therefore, this becomes a function of one variable, call it h of x. Okay, that is what 2x squared plus x squared minus 2x plus 1. I hope I wrote it correctly, just make sure. Therefore 2 into x squared minus x plus 1. Therefore what is a h dash of x equal to 0? This would imply 2x there. Okay, this 2 into 2x minus 1 must be 0. That means x must be equal to half. Therefore y is also equal to half because y is 1 minus x. So what did we do here? So I didn't need Lagrange multiplier, right? I reduced to one variable. Do you understand this trick? Yeah. But if you really pay attention, what really happened was, remember, what is our j? G is x plus y minus 1. And what is the gradient of g? G, that is 1 comma 1. This is non-zero. Therefore, by implicit function theorem, I know at least locally, here it is a linear condition, therefore it's actually globally, my g inverse 0 is a graph, okay, of this function x comma hx, x over r, right? You follow that? Therefore what I am doing is the function f, okay, this is my thing, this is the graph x comma gx, and from here I have the function for any point x, x squared plus y squared. This is my f. So that turns out to be okay, I have function x going to x comma gx, that going to f of x comma gx. Okay, but I know what is gx, therefore I get this function, therefore I get a function of one variable. Therefore actually what we did was we employed the implicit function theorem actually. Yeah, please understand, do not be overwhelmed, because if you want to understand very thoroughly you have to go deeper. Once you go deeper, okay, if your understanding is superficial you will get little worried, but don't go back and forth. Okay, again review twice, you will see you are mastered. You will see that your insight and understanding of Lagrange multiplier is far superior to many of the people around. There are a lot more examples, as I said, I don't. Now there is a third point. With that I will stop today's lecture. The third point is, let us look at again the picture. My pictures won't be good, please you have to, as usual, you know by now, you have to bear with me. Okay, this is x plus y equal to 1 line, right? This is my xy. Now what is my constraint? This constraint is this g of xy. Okay, and what is my function? F of xy, that is x squared plus y squared, right? Now what I do is I try to draw lot of level curves or level sets for this function, that is f equal to 0, f equal to 1, f equal to c, etc, so on. Okay, intuitively for all r squared is what you are doing, right? So this one, okay, this is for r equal to something, this is some other r, okay, then Now what you will see is something very interesting. Okay, this doesn't look like a circle. Okay, you will see this is the circle. Okay, you will see this circle, okay, has a tangential contact at that point where you have, I hope this is the correct one. Yeah, maybe I did something wrong there, but anyway you can do that. X equal to half, y equal to half, right? That's okay. Yeah, no, I'm doing x squared, y squared. Yeah, right. Okay. Yeah, this is the point. So what we find is at the, maybe I should do one more example. With that I will stop because my picture doesn't look see, please look at my second article, implicit functions. Their computer drawn pictures are more convincing than my stupid pictures here. Okay, yeah. So what we will find will be at the point of local, the what Lagrange multiplier says, this will be tangential. This is the level set of your G. This is a constraint. This is a constraint. Okay, and this is the level set of the function, scalar valued function. Okay, whose extrema we want to find. You will see these two touch at the same point. Okay, they touch a point, and the thing will, the tangent to this and tangent to this curve will be the same. Okay, yeah, right. So let us look at one more example. So again, f of xy equal to x squared plus y squared. My g of xy equal to x squared by y squared plus x squared by a squared plus y squared by b squared equal to 1. Let us say x squared plus b equal to, yeah, x squared plus y squared, right? So this is the thing, and as usual we will assume a is greater than b, right? This is the ellipse, this is your constraint. Now what do? I keep on drawing. Now you will see this point, some kind of local maxima minima subject to the constraint. So let me write down the constraint. This is the constraint. Okay, and these are the circles. And again I can go bigger, and finally I will get something which will be tangential to this. Again look at the article, you will see such beautiful pictures. You can see, so there are going to be 1 2 3 4, these 4 points are local extrema for the function f with the constraint ellipse, and at all the points you can see the level curve of the scalar function whose extrema we want to look at are going to be tangential to the level set at that point. Yeah, okay, fine. So why still I don't understand why the gradient comes. The gradient comes for the simple reason. Suppose yes is g inverse of 0, right? As usual, g is from, that is a u to r c1, and gradient at g at the point p is non-zero, is not 0. Okay, like that. Let's assume all those things, right? So this is my thing. It's unfortunate I can't draw. Let us assume this is 3-dimensional and this is my s. Okay, level surface or level set. Okay, this is a 3-dimensional object. Maybe I should have drawn a much better picture. Yeah, I'm not good at drawing pictures, so I can imagine, but drawing picture is always a little difficult for me. Let me try to see whether I can do that. Okay, think of this as something like this. Okay, this is our, now look at any curve, that is a curve C from some interval around 0 to r n, so that C of t always, this is, Let us assume it's also C1. C of t always lies in the surfaces. Okay, you understand? This is my minus epsilon to plus epsilon. This is my curve C, and this is my C of t. It lies, C of t lies in the surfaces, right? Right there. Then now C of t you can write as x1 of t, xn of t, or c1 of t, cn of t. They are component. Therefore, C prime of t will be x1 prime of t, xn prime of t. So this is called the tangent vector to the curve C at the point CT or CT. Okay, so this is the tangent vector. So let me assume like this. This is the tangent vector. This is C prime t at the point. This is CT, right? Now suppose my C of 0 is the point A where f has a local maxima at A, okay, with respect to S, in S. It's a local extrema with respect to only in S constraint, right? Then there is a relatively open set, okay. Okay, so my curve C, because of continuity, will lie here. Therefore, do you see that? Notice that we are assuming C of 0 is A, right? Therefore, t going to f of C of t, that is f of C of t, has a local maxima at t equal to 0. Why? Because f of C of t is f of C of t, okay, for t sufficiently near to 0, because of continuity to lie in this open neighborhood of, relatively open neighborhood of the point A in the surfaces. Yeah, therefore that will be less than or equal to f of A, which is f of C0. Okay, this lies in near A. Okay, yeah, you follow that? Therefore, what happens if it, okay, now this is a local maxima because I am in the open interval this, and 0 is an interior point, therefore I can use the first derivative test. Therefore, f composite C dash at 0 must be 0. But that is same as dff of C of 0 into C prime of 0, that must be 0. That is, this is what? This is df at A, okay, and C prime 0. But this we know this is given by gradient of f at A dot product with C prime 0 is 0. But what did we understand about C prime 0? C prime 0 is the tangent vector. It's a tangent vector to the curve, but the curve lies in here, therefore I can think of it as a tangent vector to the surfaces, to the level surface, right? Therefore, what does it mean? This fellow, the gradient of f at A must be perpendicular to that. Sorry, this is G. I am looking at level set, oh sorry, this is a level set G. I just changed the notation. This is G, so I'm sorry for the goofing. This is G. G. The level set is defined by G. Oh, I'm sorry. Okay, I'm unnecessarily getting confused. No, this is a level set is okay. I'm sorry. Let us go back. Let us go back. Okay. So what I have found is this is all right. This is f. F is a function. Therefore, I have found delta f at A is perpendicular to C prime 0. This is a tangent vector. And for a similar reason, let us look at G composite C of t. Now G is 0 on S. Therefore, this is always 0 for every t. Similar, hence delta G at A is also perpendicular to C prime 0. You understand? So del, the gradient of f at A is perpendicular to all tangent vectors intuitively, and the gradient of G at A is also perpendicular to all tangent vectors. Therefore, what do I expect? They must be scalar multiples of each other. This is my expectation. I am sorry for the goofing here. It is what I said is correct. This is f composite. I am using only f, and this is also f. Okay, whatever I said earlier was correct. Okay, so therefore I conclude the gradient of f at a is perpendicular to all tangent vectors. Since g is identically 0 on s, in particular gct is 0, all constant function, therefore by computing chain rule I will get the gradient of g at a is also perpendicular to the end. Therefore these two vectors seem to be perpendicular to orthogonal to all tangent vectors. Therefore I expect them to be multiples of each other. Okay, all these things can be rigorously proved. That is what is done in my first article, namely Lagrange theorem, a geometric treatment. Okay, so in the next lecture I am going to give a pure analytical proof which uses directly implicit function theorem, because for time constraint I don't want to go into the geometry, but on the other hand please go through it, do not get confused. Okay, if necessary read my article also, it will help you. Just ignore the last few minutes of goofing. What I wrote as F as the correct one. Okay, yeah, right. I hope in spite of my little amount confusion toward the end, all of you understood, you are intrigued. Okay, you are motivated, and also you learn you got some geometric insights about Lagrange multiplier. Okay, now let us continue. Suppose now the same notation, f is a function from u in Rn to R. This is a C1 function. Now there are k constraints gi from u to R. Okay, 1 less than equal to I less than equal to k. Right? And let's assume again, okay, and let's assume gi at a with a loss of generality is 0 for every I. Therefore I can construct this set, intersection of level sets of gi. Okay, gi of x equal to 0. So that means there are k constraints now. You understand this? So the first constraint, this is a three-dimensional space. First constraint may be s, then second constraint will be something their intersection. This may be s1, this is a constraint s2, this is s1 intersection s2, where g1 g2 they are like that. Okay, they think of this, I have something intersecting on that. Okay, right. So again you can ask, okay, suppose the point a is here, okay, and there is an open set u a in Rn, a that on u intersection yes. Where is this? As we did combined thing. Okay, intersection of all level sets, right? So on this f has a local maximum at a. Then what can I say about the gradient of f at a? Remember our idea, we want to find out the local maximum minimum of f subject to the constraint g1 to gk, right? So the gradient may not be 0 even if such a local maximum a exists, the gradient may not be 0. But as we saw in the case of one constraint, nabla fa equal to lambda times nabla ga. Okay, so if a is a local maximum, constraint maximum, then f must satisfy, a must satisfy this condition. Okay, this replaces our earlier thing, right? Okay, good. So do you think that g1 g2 gk should be arbitrary? Remember again, if you understood my implicit function theorem, what you will need is define g equal to g1 to gk, then that becomes a map from u to rk. So what do I want? I want the derivative g dga, this as rank k. This is same as saying nabla gi at a, they are all linearly independent, as we have seen earlier in the implicit function theorem case. Right? Very good. So this is the constraint. So what should be the condition then? Make a wild guess. Intuitively I know that nabla f at a must be some lambda I times nabla gi at a, on that alone, right? But it's not only on, it's not a kind of for a constraint only one. It is a combined constraint, right? So what do you think? Make a guess. Okay. So nabla f, intuitively this is not very correct because this is only with respect on SI. Okay. If A is a local constraint, local maximum of f at on SI, then only I can expect this lambda I times nabla GITA. Okay, but this is in general I cannot expect. Okay, so a very natural thing maybe is nabla f at A equals to lambda 1 nabla G1 TA and so on. That is, there exist scalars lambda 1 to lambda k in R such that. So what? Okay, this is the Lagrange multiplier theorem. So let us formulate the theorem and stop here, and we'll complete the proof tomorrow in the next lecture. So let U be open in Rn. Okay, F from U to R be C1, and let G equal to G1 to Gk be from U to Rk be C1. Assume that. Okay. Derivative of G at A, let us assume A belong to A in U. Nabla J has rank K. Okay. I assume further that okay F has a local maximum or minimum at A on S, which is G inverse of GA. If I assume GA equal to 0, this is G inverse 0. Okay, keep the picture in mind. So it's something like G1A may be some kind of a surface, G2 inverse of 0 will be another surface, so you're on the intersection. Okay, that is our S. Do all of you understand that? Yeah. Okay. Right. Then what do you want to say? Then there exists scalars lambda 1 to lambda k in R such that the gradient of f at A is a linear combination of gradient of G1 at A plus lambda k gradient of Gk at A. This is what the theorem says. Okay. The proof, as I said, is a very easy application of implicit function theorem. Okay, we will do that, and after that perhaps we will also give one application. Okay, yeah, please go through this. Okay, so what are the general assumptions? Yeah, maybe I should say something more. Yeah, what is the geometric intuition for this? Again, think of this. I can define a curve C from some interval epsilon to S, but I think of S sitting in U, which is sitting in R. So therefore this curve is C1. Okay, if you want this C and C cancels, let me look at it. Gamma is a curve. This is a C1 curve. As a function from the interval to this, what is the condition? Gamma 0 is A. Okay, that's it. Okay, again I will write S as a surface, but okay, so this is my U, this is my S, and this is my A. Okay, sorry, maybe let me take this as A. This is the curve, gamma. And 0 goes to A, right? Therefore, as we did again, gamma T I can write as so gamma T I can write as x1 of T xn of T. Therefore, gamma prime 0 is x1 prime 0, x1 prime 0. This is the tangent vector, right? So what we can do is, if I compose f gamma of t, okay, this is a function from minus epsilon to plus epsilon to, yeah, do you remember this? This is going to be r, and this is c1, and f composite gamma of 0 is greater than f composite gamma of t. Okay, if I choose epsilon in such a way that the whole thing falls in some open set containing a. Okay, remember local maxima minima I have to use for that. Okay, is it okay? I can assume this for every t, or cut down epsilon small. Therefore I know f composite gamma prime 0 must be 0, because this is a local maximum for this real valued function of a real variable. But that would mean df gamma of 0 acting on gamma prime 0, that is nabla f at a dot product with gamma prime 0 is 0. So as earlier, again nabla f at a is perpendicular to any tangent vector. Okay, right? And now let's look at lambda g. The same thing happens, because g composite gamma is identically 0. Therefore dg at a acting on gamma prime 0, this is also 0. Okay, so what we do is, the set of tangent vectors to S at A is precisely kernel of the map DGA. Okay, so you have something like Rn, and this is your kernel of DGA. So you follow that? Yeah. Now our vector nabla A has to be linear combination nabla F at A. Okay, that is also orthogonal to this. Okay, so what we do is the thing, that means nabla GA at A is perpendicular to all tangent vectors, and so is nabla F at A, all tangent vectors. So using linear algebra, from this we will conclude lambda F at A is linear combination. Okay, for this geometric proof, you just see my article on Lagrange multiplier, geometric treatment. Okay, so I will actually prove this. So I will explain what is meant by tangent vector, and I will prove that. But as I said, this is not the approach I am going to take in the next lecture, where I will directly prove this Lagrange multiplier theorem. Okay, so let us look at that. If gamma, I think the tablet was not shown, the screen was not shown. So as earlier we saw that nabla F at A is perpendicular to tangent vector. It's the same case as the origin, the earlier one, with one constraint. Now let's look at the second constraint. That's also same, because g comes with gamma is 0, because g is 0 on S. Therefore g comes with gamma is 0. That means dg a. Okay, if I take g comes with gamma prime 0, that must be 0, but that is equal to this. That means gamma prime 0 lies in the kernel of dga. In particular, each of the gradient del gi at A must be perpendicular to tangent vectors. Okay, so in the geometric treatment of Lagrange multiplier, I actually prove the set of tangent vectors equal to kernel of dga. Using linear algebra, from that we can conclude this. Okay, but as I said, tomorrow we will give a more direct analytical proof that will be easier for many students to follow. Okay, stay safe, take care, we will meet again.